guys, welcome to Applications of Integrals of 7 Volumes with Known Cross-Sections. So in this section, we're going to look at what happens when you take some base and you try and build a solid on top of it. And you build that solid by taking known cross-sections. And what we mean by that is essentially you're going to take some shape and you're going to build that shape on top of the base in exactly the same proportion every time. So take this this picture here. Imagine that if I took this piece that's been cut and put it back where it started. We'd imagine that the bottom would essentially be a rectangle, right? Well, this rectangle on the bottom would be the known base, right? And then on the inside, we essentially have this top part here is essentially a known cross-section. Regardless of where I cut this, we can imagine that we would have a bunch of semicircles, right? That's essentially what we're doing. It's not exactly what we're doing, but it's essentially what we're doing. We have some kind of base, and then on top of that, we're building a bunch of cross-sections that are some known shape. And regardless of where in the shape I am, I'm going to have the exact same cross-section. Okay? So let's take a look at how that works. Okay, so example 1. Find the volume of the solid whose base is the circle x squared plus y squared equals 25, and whose cross-sections perpendicular to the x-axis are, in the first example, squares, and in the second example, equilateral triangles. Okay? So we can see here the base is going to be a circle, and then on top of that circle, we're going to build a bunch of squares. The idea is that wherever on the circle you are, that's how big the square is. So we can see here that because this part of the circle is smaller, we have a shorter square, right? And then in the middle, where we have the diameter, which is the largest size, we're going to have the very largest square, right? And then we can imagine that over here, we would have again, it would get smaller, so we would have a shorter square, okay? And if you guys remind me in class, I do actually have a model of this that you guys can see, so hopefully that will help, okay? Alright, so let's give the problem a try. Alright, so the idea to this is that what we want to do is use what we know about these volume type problems to build our answer, okay? The first thing that we're going to do is we're going to start by figuring out what's the length of one of these sides, okay? These are perpendicular to the x-axis, so we're going to go from top to bottom, right? Working along one of these sides to figure out what one side length is going to be, right? So if we're going from here to here, that would be, right, top to bottom would be in x, right? Anytime you're working perpendicular to the x-axis, that would mean that you're going to be, right, top to bottom works in x, so we're going to be integrating in x. So I'm going to figure out that y is equal to plus or minus, right? If I were to move x to the other side, take the square root of 25 minus x squared. That's a 2, really it is. So that gives me actually two functions. It doesn't seem like it, but it really is. This top function, which that works miraculously well, is going to be the positive square root of 25 minus x squared. And then on the bottom, is going to be the negative square root of 25 minus x squared. Right? So then what happens is this green arrow is traveling from the positive square root to the negative square root. So this one side length of the square is actually, and it would be the same for any of them, right? That side length or this side length, or even the little teeny tiny side length, right? Any of those is going to be, one side is going to be the square root of 25 minus x squared minus negative square root of 25 minus x squared. Or minus minus becomes plus plus, which is 2 times the square root of 25 minus x squared. Okay? So that's one side. Okay? Now, that's great, but we don't really care about one side. What we care about is the area, right? Or at least I'm going to tell you that's what we care about for now. So let's see if we can figure out the area. Okay? So if I could find the area of one of these guys, right? That shouldn't be too hard to find. These are squares after all, right? So the area of one of these squares, right, would be the side length squared, right? And the side length being 2 times the square root of 25 minus x squared, squared. 2 squared would be 4. And square root of 25 minus x squared squared would be 25 minus x squared. Not so bad. Okay, so that's the area. Well, if that's the cross-section, right, what have we learned from doing discs and shells and all this other stuff, right? Well, what we've learned is that we take this and we apply some infinitely teeny tiny thickness to it, and then we integrate over the entire circle, right? So my circle goes from way over here at -5, if you can still see that, and over here to 5. So we're going to take, so our volume is going to be the integral from -5 to 5 of the area dx, right? Oops. So we're going to have the integral from -5 to 5 of 4 times 25 minus x squared dx. And I plugged that in and I got 2,000 thirds. Whatever that comes up to. So there you go. Let's try this with equilateral triangles. Okay. So kind of a funny picture, right? But very similar picture, right? Again, we see teeny tiny triangle over here because, well, it's a smaller side over here. Big triangle in the middle because it's over here. In the middle where we have a larger space, basically, right? Okay. Okay. Same idea, right? Perpendicular to the x-axis, so we're going to integrate in x. Okay. And then this top part here, right? This top part here is square root of 25 minus x squared. The bottom part is negative 25 minus x squared. So the side length is still 2 times the square root of 25 minus x squared. That part has not changed since we did this in the first part of the problem. What has changed is the area. We're not dealing with the area of a square anymore. We're dealing with the area of a triangle. And in fact, the area of an equilateral triangle. So you may or may not recall that last year I forced you guys to go through this memorization, about 1,500 of these stupid formulas. And one of them was the area of an equilateral triangle. And you may or may not have remembered this. Hopefully you do. The area of an equilateral triangle is s squared root 3 over 4. There's a reason I made you memorize this. It's not just for my entertainment. It is because you actually have to know these. S squared root 3 over 4. So, the area is going to be, well, take this and plug it in. We're going to have root 3 over 4 times 2 root 25 minus x squared squared, which will give us root 3 over 4 times 2 squared is 4 times 25 minus x squared. 4 and 4 cancel. Well, that's convenient. And we get root 3 times 25 minus x squared. Cool. Alright. So, volume equals root 3 times the integral from negative 5 to 5, 25 minus x squared dx. Nothing to it. I plugged that in. I ended up with 500 root 3 over 3. Not too bad. Hope. Right? Okay. Example 2. Alright. Find the volume of the solid whose base is the region enclosed by the lines x equals 0, better known as the y-axis, y equals 0, better known as the x-axis. I always find that confusing, but okay. I don't know if I should. Okay, that did not work. I'm just, you know what the y and the x-axis are. And y equals 2 minus 0.5x, which is of course the slanty line over there, and whose cross sections perpendicular to the x-axis are semicircles. Okay, so we get this kind of picture right here. All right. So, what do we do? Same thing. Okay. So the first concept we want to think about, just like before, is that these. Okay, let's try straight lines. These things coming down, right, create sides. Okay. So this should be easy enough. The side is 2 minus 0.5x. I'm going to write it as 1/2 x. I'm not a big fan of decimals. Right? Minus 0, because that's 0. So we don't need to write that. Okay. And now we want to try and find the area, right? We want the area of one of these semicircles. Now, area equals pi r squared for a circle. But these aren't circles. These are semicircles. So I'm not going to write it as pi r squared. I'm going to write it as 1/2 pi r squared, right? Semicircles being half of a circle. But we have a problem here. Unlike the last problem, I cannot take the side and just plug it in for r, because it's not 1/2 pi side squared. It's 1/2 pi r squared. And each of these sides are not a radius. Each of these sides are, in fact, a diameter, right? If I were to go like this, that would be a radius. So each of these sides are twice the radius. So in order for me to make this work, I need to figure out what the radius is. In other words, I need to take one of these sides and cut them in half. Okay, I can do that. So I can either just say 1/2 2 minus 1/2 x, and plug it in and get more constants, or I can just figure out what that is. In this case, it's easy enough to do that. In other problems, you're going to want to leave it as 1/2 and let it work itself out, right? So in this case, 1/2 times 2 is 1, minus 1/2 times 1/2 is 1/4 x. And that comes out pretty nicely, so I'm just going to leave it. If you decide not to do that, notice that you'll get 1/2 pi times 1/2 side and squared. 1/2 squared is 1/4 side, and 1/2 times 1/4 squared. 1/2 times 1/4 is 1/8. So you'll get 1/8 pi side squared. Okay, so this problem tends to come up a lot. So just be forewarned, either semicircles or full circles, and be forewarned that there's nothing wrong with doing this. Okay, should you choose to do that, but I choose not to do this. I just want to forewarn you that this is an option that you can choose. Okay? Alright, but since I have chosen not to do that, I'm going to come back to here and say 1/2 pi, and the radius, which is 1 minus 1/4 x squared. I'm not going to square that because that's ugly, so I'm just going to take the integral. And our volume, right, this is in x, so I'm going to go from 0 to 4, okay. 0 to 4, I've got a 1/2 pi, and 1 minus 1/4 x squared dx, and toss that in the calculator. I got 2 pi over 3. And that's it. Nothing to it. Oh, sorry, I have my cell phone right here, and hopefully you guys didn't see that. Okay, hear that. Although I'm guessing you probably did. Let me turn that off here. Okay. Alright, and last problem is almost the exact same thing. Find the volume of the solid whose base is the region enclosed by the lines x equals 0, y equals 0, and 2 minus 0.5x. So same exact base, whose cross-sections perpendicular to the y-axis are semicircles. And I was not able to find a picture on the internet for this. But I'm basically looking for the exact same thing, but now the semicircles are basically just going the other way. I'm going to get rid of these semicircles because I think they're just distracting. We all know I can't draw, okay? The idea is that now your semicircles are just headed in this direction, okay? Same concept, different direction. Okay, so what do? Well, now if you're going perpendicular to the y-axis, you're going to have your integral dy instead of dx. And if you're going to have your integral dy instead of dx, that means you need to take, that means you need to rewrite this guy in terms of y. Okay, not too bad. So we flip this around, we're going to have, I hate decimals, we're going to have 1/2 x equals 2 minus y. And multiply by 2, x equals 4 minus 2y. Okay. Same concept. So for my first job is to find out one side length, right? Make a semicircle here. So one side length would be, right, now we're going from here to here. I don't know why I bothered trying to draw pictures. Okay. Do it in green. So one side length, right, going from there to there, is 4 minus 2y. Right? And our next job, find the area. Right? And remembering the area is pi r squared for a circle, but it's not pi r squared, it's 1/2. Okay. It's going to be 1/2 pi r squared because it's a semicircle. And then we go, oh, but wait, it's not r that we have, it's s because that's a diameter, right? And we want a radius. So we need to take s and cut it in half. So we're going to cut it in half. We're going to say 1/2 times 4 minus 2y, which is going to give us 2 minus y. Okay. And so then we're going to plug that in, and we're going to get 1/2 pi times 2 minus y squared. And once we have the area, all we have to do is integrate. Remembering that we're integrating in y, not in x. So we're going from here to here instead of in the other direction. And that's the y-intercept. The y-intercept is 2. So we're going to go from 0 to 2. 1/2 pi, the pi on top there, 2 minus y squared dy. And I got 4 pi over 3. And I plugged it in. Okay. So there you go. That's all I got. And we are done with applications of integrals. So I will see you guys tomorrow.